A remote island in the southwest Indian Ocean is quietly redrawing its own boundaries, one lava flow at a time. Along a stretch of coastline where black volcanic rock meets open water, new land is forming in plain sight, extending shorelines outward by meters and over longer intervals by distances measurable in both hundreds of meters and fractions of a mile. How often does a place quite literally grow before the eyes of those who monitor it? What processes allow molten rock from deep within the earth to harden into solid ground within hours or days? And how much of this expansion is visible today compared to the vast accumulation that has taken shape over thousands of years? At the centre of this activity is Réunion Island, a French overseas region positioned east of Madagascar and one of the most volcanically active locations on the planet. Its defining feature, Piton de la Fournaise, ranks among the world's most active volcanoes, erupting frequently with lava that is typically fluid, basaltic, and capable of travelling long distances before cooling. Unlike explosive volcanic systems that dominate headlines elsewhere, this volcano tends to produce effusive eruptions, where molten rock pours steadily from fissures and vents, advancing across the landscape in glowing rivers that can reach speeds measured in several kilometres per hour or a few miles per hour under favourable slopes. The most recent eruptive phase, which began in early 2026, has continued this long-established pattern. Lava has emerged from fissures on the volcano's flanks, descending through channels carved by previous eruptions and spreading across the lower slopes. In certain sectors, flows have advanced all the way to the coastline, where they meet the ocean in a dramatic but methodical interaction. Upon contact, seawater rapidly cools the molten rock, forming new layers of solid basalt. These layers accumulate outward, extending the island's perimeter by distances that can range from several meters in a single event to more substantial additions over successive eruptions. Measurements taken from satellite imagery and ground-based monitoring systems indicate that recent flows have added strips of land tens of meters wide along specific coastal sections. In imperial terms, this corresponds to expansions of roughly several dozen yards, with localized protrusions extending farther depending on terrain and lava supply. While these increments may appear modest when viewed individually, their cumulative effect over repeated eruptions is significant. Over decades, the coastline has advanced outward by distances approaching several hundred meters, or over 1,000 feet in certain areas, fundamentally altering the island's shape. The mechanics behind this steady growth are rooted in the geological engine beneath the island. Réunion sits above what geologists identify as the Réunion hotspot, a plume of abnormally hot material rising from deep within the Earth's mantle. This plume supplies magma continuously, feeding volcanic activity at the surface. Unlike tectonic boundary volcanoes, which are driven by the interaction of moving plates, hotspot volcanoes remain relatively fixed, while the overlying tectonic plate shifts slowly above them. This process creates chains of volcanic islands over geological time, with older islands drifting away from the active hotspot and gradually becoming dormant. In the case of Réunion, the hotspot remains directly beneath the island, sustaining ongoing volcanism. The magma generated here is predominantly basaltic, characterized by low viscosity, which allows it to flow easily compared to the thicker, more silica-rich magmas found in stratovolcanoes. This fluidity is a key factor in the island's expansion. Instead of building steep, unstable cones, the lava spreads outward in broad sheets, creating the gently sloping profile typical of shield volcanoes. Each eruption adds another layer, incrementally increasing both elevation and horizontal extent. The journey of magma from its source to the surface involves a complex network of conduits, fractures, and storage zones. Beneath Piton de la Fournaise, seismic data and deformation measurements reveal a system of magma reservoirs located at varying depths, from several kilometers below the surface to shallower chambers closer to the summit. Pressure builds within these regions as magma accumulates, eventually forcing its way upward through fractures. When the pressure exceeds the strength of the surrounding rock, fissures open, allowing lava to escape. During the current eruptive phase, monitoring instruments have recorded ground inflation preceding the eruption, followed by deflation as magma was released. This pattern aligns with previous events, reinforcing the understanding of how magma moves within the volcano. Lava output rates have varied throughout the eruption, with peak discharge measured in tens of cubic meters per second, equivalent to several thousand cubic feet per second, before tapering off as the eruption progressed. Estimating the total volume of magma erupted during this ongoing activity presents challenges. While preliminary figures suggest that millions of cubic meters, equivalent to tens of millions of cubic feet, of lava have been emitted since the start of the event, precise totals for the entirety of 2026 remain under evaluation. Continuous eruptions, pauses and reactivations complicate cumulative measurements, and official consolidated figures typically require post-eruption analysis. What is clear, however, is that the volume already in place is sufficient to produce noticeable changes along the island's margins. When lava reaches the ocean, the interaction triggers rapid cooling and fragmentation. Steam plumes rise as seawater flashes to vapor, and the outer surface of the lava solidifies almost instantly, forming a crust. Beneath this crust, molten material continues to flow, creating unstable structures known as lava deltas. These newly formed land extensions can collapse without warning, as their base is often composed of loose, fragmented rock rather than solid bedrock. Even so, repeated emplacement and cooling eventually stabilize portions of these deltas, incorporating them into the island's permanent structure. Over longer timescales, this process has played a central role in shaping Réunion. Geological mapping shows that much of the island's present-day area was built through successive lava flows reaching the sea and extending the coastline outward. In some regions, ancient lava deltas have become indistinguishable from older land, their origins preserved only in subsurface structure and rock composition. The Réunion hotspot has been active for tens of millions of years, leaving a trail of volcanic features across the Indian Ocean. This trail includes submerged plateaus and island chains that mark the path of the tectonic plate as it moved over the stationary plume. Among these features is the Deccan Traps region in present-day India, formed approximately 66 million years ago, when the hotspot's activity was far more intense. Although the current output at Réunion is modest by comparison, it represents a continuation of the same fundamental geological process. Within the island, volcanic activity is concentrated primarily at Piton de la Fournaise, while an older volcanic structure, Piton des Neiges, remains dormant. The contrast between these two systems illustrates the life cycle of hotspot volcanoes. Piton des Neiges, once active, has ceased erupting and is now deeply eroded, its high peaks reaching elevations of over 3,000 meters, or nearly 10,000 feet above sea level. In contrast, Piton de la Fournaise continues to build upon itself, with each eruption contributing to its height and lateral expansion. The current eruption has also highlighted the efficiency of modern monitoring systems. Satellite-based thermal imaging detects hotspots on the volcano's surface, while ground instruments measure seismic activity, gas emissions, and ground deformation. These datasets provide a near-continuous picture of the eruption's evolution, allowing scientists to track lava flow paths, estimate discharge rates, and assess potential impacts on nearby areas. Despite the volcano's frequent activity, the risk to populated regions remains relatively limited due to the predictable nature of its eruptions and the presence of designated hazard zones. Lava flows typically follow established pathways toward uninhabited coastal areas, reducing the likelihood of direct impact on infrastructure. However, the creation of new land at the coast introduces additional considerations, including changes to marine ecosystems, coastal erosion patterns, and navigation hazards. As lava continues to flow toward the ocean during this eruptive phase, the island's outline is being subtly but measurably altered. Each new layer of basalt represents a permanent addition, a solidified record of molten rock that originated deep within the Earth's mantle. The process is incremental, often unfolding over days or weeks, yet its cumulative effect is profound. Over years, decades, and centuries, these additions reshape the island, extending its reach into the surrounding ocean and reinforcing its identity as a dynamic, evolving landmass. The ongoing activity raises further questions about the future trajectory of the island's growth, the continuation of magma supply from the hotspot, and the long-term balance between construction and erosion that ultimately defines volcanic islands. The outward growth now visible along sections of the coast is only the most recent expression of a process that operates across vastly different timescales. While individual lava flows may extend the shoreline by several meters in a matter of days, the full construction of Réunion Island reflects the accumulation of countless such events layered over hundreds of thousands of years. Each new deposit of basalt adds not just width to the island, but also thickness, reinforcing earlier constructed surfaces and gradually elevating them above sea level. In certain regions, stacked lava flows have reached thicknesses of several hundred meters, or over 1,000 feet, forming a strong foundation that resists wave erosion more effectively than the loose material created during the earliest phases of ocean entry. During the ongoing eruptive cycle in 2026, remote sensing data has continued to refine estimates of lava production. Thermal anomaly measurements combined with volumetric modelling of flow fields suggest that the eruption has already generated on the order of several million cubic meters of lava, equivalent to tens of millions of cubic feet. Some preliminary range assessments place the cumulative volume closer to the lower tens of millions of cubic meters when accounting for multiple active phases earlier in the year, though a definitive figure will only be finalised after post-eruption mapping is complete. Even at the conservative end of these estimates, the quantity is substantial enough to alter both topography and coastline geometry in measurable ways. The distribution of this material is uneven, reflecting the influence of slope gradients, pre-existing lava channel networks, and barriers formed by older flows. On steeper upper slopes, lava tends to move rapidly, forming narrow, confined streams that can travel several kilometers or a few miles before spreading. As the terrain flattens closer to sea level, these flows broaden, slow, and thicken, creating extensive fields of solidified basalt. In some sectors, overlapping flows have built up terraces that extend outward step by step, each layer marking a separate eruptive pulse. Where these flows intersect the ocean, the mechanics of land construction become especially pronounced. The front edge of a lava flow entering seawater often fragments into angular blocks, which accumulate to form a base for subsequent lava to advance. This creates a constructed platform that gradually extends seaward. Over time, repeated emplacement fills in gaps, reduces instability, and transforms initially fragile lava deltas into consolidated land. Measurements along active entry points during the current eruption indicate outward growth rates that can reach several meters per day under sustained high discharge conditions, equivalent to roughly 10 to 20 feet daily in localized sections. Yet this expansion is not continuous or uniform. Episodes of collapse frequently interrupt the process, particularly when newly formed land extends too far beyond stable support. Sections of the lava delta can suddenly fail, sliding into deeper water and generating small explosion-like interactions as hot rock meets ocean water at depth. These events remove portions of the newly created land, effectively resetting the growth cycle in those areas. Even so, the net balance over multiple cycles typically favors expansion, as subsequent flows rebuild and extend beyond previous limits. Beneath these surface dynamics, the supply of magma remains governed by the deeper workings of the Réunion hotspot. Geophysical data indicate that the plume continues to provide a steady flow of hot material into the underlying lithosphere, where partial melting generates basaltic magma. This magma accumulates in reservoirs beneath Piton de la Fournaise, feeding eruptions through a system that has shown remarkable consistency over recorded history. One notable aspect of this system is the relatively short interval between eruptions. Piton de la Fournaise has been known to erupt multiple times within a single year, with repose periods sometimes lasting only a few months. This frequency allows for a near-continuous addition of material to the island's surface. In the context of 2026, the current eruption is part of a broader pattern of activity that has included earlier eruptive episodes, each contributing incrementally to the overall magma output for the year. Gas emissions associated with the eruption also provide insight into the volume and nature of magma involved. Measurements of sulfur dioxide output, often expressed in tons per day or metric tons per day, have fluctuated in tandem with lava discharge rates. Peaks in gas emission typically correspond to higher output rates of magma, offering a proxy for estimating eruptive intensity. While exact cumulative gas totals for the year remain under compilation, the observed levels align with moderate effusive eruptions rather than exceptionally large events. The structural evolution of the volcano itself is closely tied to these eruptive cycles. As lava accumulates on the flanks, it alters the stress distribution within the edifice, influencing where future fissures may open. Ground deformation data from 2026 shows localized inflation preceding eruptive events, followed by deflation as magma was released. This cyclical pattern reflects the dynamic balance between magma supply and output, a process that continuously reshapes the internal architecture of the volcano. Beyond the immediate vicinity of the eruption, the broader geological framework of Réunion continues to evolve. The island's position above the hotspot means that it remains in an active phase of construction, unlike older volcanic islands that have drifted away from their source of magma. Over geological timescales, this sustained activity can lead to significant increases in both area and elevation. Current estimates place the island's total surface area at approximately 2,500 square kilometres, or around 965 square miles, a figure that has grown incrementally through successive eruptions. However, construction is only one side of the equation. Erosion acts continuously to counterbalance volcanic growth, particularly in regions not reinforced by recent lava flows. Rainfall, which is among the highest recorded globally in certain parts of the island, drives intense fluvial erosion, carving deep valleys and transporting sediment toward the coast. Coastal wave action further reshapes the shoreline, removing weaker materials and redistributing volcanic debris. The interplay between these constructive and destructive forces determines the island's long-term morphology. In the regions affected by the current eruption, the immediate impact on marine environments is also under close observation. When lava enters the ocean, it alters water temperature and chemistry locally, introducing minerals and particulates that can affect marine ecosystems. While these changes are typically confined to the vicinity of the entry point and diminish with distance, they represent an important aspect of the island's ongoing interaction with its surrounding environment. Navigation and coastal management considerations also arise from the formation of new land. Newly extended coastal sections may not appear on existing charts, creating potential hazards for vessels operating near shore. Over time, updated mapping incorporates these changes, but the speed of volcanic construction can outpace traditional surveying methods. Satellite-based mapping has become an essential tool in addressing this gap, providing near real-time updates on coastline configuration. The continuation of eruptive activity in April of 2026 suggests that additional volumes of lava may yet be added before the current cycle concludes. Each subsequent flow has the potential to extend existing lava fields, reinforce newly formed deltas, or open entirely new pathways toward the sea. The exact trajectory of these developments depends on factors including magma pressure, structural weaknesses within the volcano, and the evolving topography shaped by earlier flows. Taken together, the events unfolding at Piton de la Fournaise illustrate a rare opportunity to observe land construction as an active, measurable process. The island's expansion is not a theoretical concept confined to geological past, but an ongoing reality documented through modern instrumentation and direct observation. Each cubic metre of lava that cools into solid rock represents a tangible addition to the island, a permanent modification of its boundaries that will persist long after the current eruption subsides. Over extended timescales, the implications of this growth extend beyond the island itself. The continued activity of the Réunion hotspot ensures that volcanic construction will continue as long as the plume remains active beneath the region. While the rate of growth may fluctuate, the underlying mechanism shows no indication of ceasing in the foreseeable geological future.